Hello, ladies and gentlemen. Okay, I hope that at least you can listen to the recording. Okay, if you are not able to get online. Uh, okay, I will start the class right now, and whenever you log in, you will join our lecture, or you can listen to this recording at your convenience. Okay, today we are going to cover module 5, which is on the fourth chapter of sampling distribution um, uh, and normal distribution approximation. Okay, we here in this chapter, it's important. It lays a foundation for inferential statistics because we are talking about the sampling distribution of sample statistics, like sample mean or sample standard deviation, sample variance. Okay. We with this and with the help of central limit theorem, we are able to approximate the sampling distribution or sample statistic to normal distribution, and this is very important because then normal distribution can be used in our inferential statistic, and because without this without establishing this approximation, the inferential statistic will have no solid ground. Okay, and so this chapter is serve as a hinge, like a hinge of a door. If a door has no hinge, then it cannot be opened or closed. Okay, so okay, and I only need you to cover chapter 1. I mean sections 4.1.1 and 4.2, 4.1 and 4.2 and 4.4. So we will just cover these chapters. Okay. Not sections. Sorry. Okay. Here, what does it say is this theorem says that x1, let me see if I could, okay, make it this bigger. Okay. Here, theorem 4.1.1 says that x1 to xn be a random sample of size n from a population with mu and the variance sigma square. Okay, then the expected value of x bar is equal to mu and variance of x bar equal to sigma square over n. So these are the steps that this can be verified, can be proved. So with that, you can see that the expected value of x bar is the expected value of is the expected value of 1 over n times the summation of all the xi. Then you can take all the constant out and the summation outside, and then just leave the x in there. But the expected value of xi is of the random variable is just the mu. Okay, so then you have summation of n mu divided by n is mu. Okay, so the mean is the same, but the variance will be decreased. Why? Because if we do the same thing to the x bar and x bar equal to that, to take that n outside of the variance, you have to square it. Then it's a summation of all the variances of the different xi's, and that gives you n times sigma square. But n times sigma square divided by n square give you sigma square over n. All right. Okay. Okay. So that is the variance. The variance. So here now then there is another theorem called Chebyshev inequality. Chebyshev inequality. And Chebyshev inequality says the probability, Chebyshev, excuse me, basically it says this can be used to, let me see, become more and more. Okay, the implication of 4.1.1 is that the sample means become more and more reliable as the estimate of mu and as the sample size is increased. Okay, and as we would expect. Okay, from Chebyshev, we let me see. This one is used for later to prove the normal, the central. We can be used to prove in the central limit theorem section. Okay, so we will skip this one for now. Okay, let's go scroll down to 4.2. Okay. Central, let's look at the sampling distribution associated with the normal populations. Okay. The result of this theorem here is that the moment generation of no random variable with mean that and the variance that. Okay. Then the following result, then we have following result, okay, which says that x1, x2, x3 to xn be a random sample of size n from a normal population with mean mu and variance sigma square. Then, okay, here it says normal population with mean mu and sigma square. Then x bar equal to that, we know. And then this is normally distributed with the center. Okay, mu x bar is the center, is the same as the population distribution, and its variance is equal to that divided by n. Okay, so this is the central limit theorem. Central limit theorem. Okay. In other words, recall that we have used the notation n follows and x follows normal distribution with the mean mu and variance sigma square, and x is normally distributed with mean mu and variance sigma square. Then what about x bar? Look, what we care for is the distribution, okay, of sample mean, because then we can make any arbitrary population distribution, regardless of the population distribution, through the central limit theorem. We can we don't worry about the population distribution, because through the central limit theorem, its sampling distribution or sample mean always follows the normal distribution if the sample size is large enough. Okay, if n is large. Okay, and hence by the Z transformation would be, obtain the standard normal like that. Okay. So the difference between this chapter and previous chapter is that its standard deviation is decreased by the scale of square root n. So sigma divided by square root n will be its standard deviation. Okay. Right. So this is a central limit theorem. Later you may have an we may go there and see the proof. Okay, so the biggest difference is in the question for this section is that you use the same method you did for when you have normal distribution, but you use the sigma over square root n instead of sigma. Whenever you see x bar as the random variable. Okay, so previously we have x as a random variable. Now we are interested in x bar as the variable. Okay. Okay. So for this question, you see that a company that manufactures cars claims that the gas mileage is for its new line of hybrid cars on average is 60 miles per gallon, and standard deviation 4. So this means x follows normal. We call the average 6. Okay, it doesn't have to be normal. Okay. And then a random sample of 16 cars yielded a mean 57 miles. Okay, if there's only 16 cars, then the population distribution has to be normal. Okay. If a company's claim is true, what is the probability that the simple mean is less than or equal to 57 miles per gallon? What assumptions did you make? Okay, the assumptions you make, given the sample size is small, then you will assume that it's quoted from the normal distribution. Okay. Yeah, here you see that. Here we have assumed that the 16 come from a normal population. So we could apply the result. Otherwise, it has to be 30 or higher because 16 is not large. Okay. So, okay, you have, this is the question. You translate your question into this and do a standardizing, and then you can use Excel or StatDisk. You can both calculate the result or using a table. Okay, you will be able to calculate the probability, which is very, very small. Okay. All right. And let me see. Let's skip to 4.4. Section 4.4. Okay, let me show you 4.1.10 first, because that's a question. I think your assignment question, right? Let me see. What is your? Sorry. Let's see assignment 1 question. Assignment 5. Assignment 5 question 4110 and 4410. Okay, so 4110. Let's go to 4110. 5110. Okay, fine. The textbook. Okay, sampling distribution. Okay, let's go to 4110 and take a look. Oh, by the way, this week I don't give you a whole lot of questions because then you need to prepare for the midterm project for using R on central limit theorem. Okay, and here it says an image encoding algorithm, when used to encode images of a certain size, uses a mean of 110 milliseconds with a standard deviation of 15. So you have a mean mu equal to 110, and standard deviation is 15 milliseconds. So what's the probability that the mean life? So this mean life means x bar. So whenever you talked about x bar, we shall consider the sampling distribution of the sample mean. Yeah. Okay. In other words, x is a random variable instead of x bar. I mean, x bar is a random variable, not x anymore. So in that case, n shall play a part in the denominator. In the denominator, yeah, which has to go along with the sigma, and n is 50. So so you are to calculate the area between 90 and 135 seconds. So what assumption you have to make? This assumption you have to make is that 50 randomly selected image size. Okay, here since you have the 50 randomly selected image, okay, so basically you don't have to make a normal population assumption because you have a large sample size. Okay, so what you need to do is just to use the method, but include the n in the calculation. So what you do is like this. Okay. Do it here. Okay, so for this question, and what you should do is, what the question is, mu is what? 110. Standard deviation is 15. Now, n is 50. So what is your mu x bar? It should be equal to mu. What's your sigma x bar? That means the sampling, the mean of the sampling distribution of x bar is equal to mu. And then the sampling distribution of sample mean, the standard deviation of sampling distribution of sample mean equal to what? Sigma over square root n. Here is mu. Here it is mu. Okay, n over that. Okay, so with that, you should be able to calculate x bar between 90 and x bar and 135. So you just follow the example previously and plug in this and that, and using z equal to x bar minus mu x sigma x bar, right? And then standardize this to, okay, and then you can go further using Excel or table to solve for this question. And as I mentioned, there is no need for assumption because already it's a large sample size. Okay, so this is the first question. Okay, all right. Now let's move on to 4.4. 4.4. Okay, 4.4 is here. And okay, here we talked about the approximation. Approximation means that we use, okay. Let me make it bigger. Okay, normal approximation to binomial distribution. Okay, suppose y is a binomial random variable. And this random variable has parameters n and p is the probability of success. And it can be viewed as a number of successes in n trials, can be written as where x is the result of one or zero. Actually, x follows the Bernoulli distribution because no binomial distribution is a series of Bernoulli distribution. You combine n Bernoulli distribution, you get binomial distribution with n trials. Okay, so so now with this, and we will see that a fraction of the successes in n trial, it means y is the number of successes and n is total number of trials. So that's a fraction, that's a proportion, that's a percentage. It's relative frequency. Okay, the relative frequency as a probability, as a fraction of successes is denoted by x bar. Okay, x bar. So now that, you do simple, this is a, y over n is a sample mean, but the expected value of xi is a p, and because x is a Bernoulli, so it's the expected value of Bernoulli is p, and then variance is pq. Okay, so we have the expected value of y over n equals to this, but then you take out a 1 over n and the sum of all, and take out the n and the summation, 1 over n and the summation times the expected value of xi, but the expected value of xi is n times p. So n times p divided by n, you get p. So that means the expected value of x bar equal to p, and expected value of x bar, which is y over n, equals to pq over n, or p 1 minus p, p times 1 minus p over n. Okay, so this is approximation. That means you, okay, oh, look at here. Okay, in this example, if you are going to use a normal approximation for binomial, then we use the mean of the binomial distribution, which is n times p, and then divided that by square root npq. We should continue to finish here, because y equal to n times x bar, but this is n times x bar, but x bar give you p, so y equal to mp, and okay, by the central limit theorem, y has an approximate normal distribution with mean mu equal to n mu and variance sigma square n times p times 1 minus p. Okay, and the normal approximation to this binomial is widely used. Okay, but in order to use this, you need to make sure that n is large enough so that np greater than equal to 5, nq or n times 1 minus p greater than or equal to 5. Okay. Okay, so you use that to approximate binomial, to use the result of a normal distribution of to approximate binomial, and follow this formula. Okay, follow this formula. Okay, let me see. So if we look at this example, a study of parallel interchange ramps reveal that many drivers do not use the entire length of parallel lanes for acceleration, but seek as soon as possible a gap in the major stream of traffic to merge. At one site on Interstate Highway 75, 46% of drivers use less than 1/3 of the lane length available before merging. Suppose we monitor the merging pattern of a random sample of 250 drivers at the site. What is the probability that fewer than 120 of the drivers will use less than 1/3 of the acceleration lane length before merging? Okay, so this is a binomial type of question where you have n equal to 250, you have p equal to 0.46. So first calculate the mean of this binomial. You get np is 250 times 0.46, you get 115, and n times 1 minus p, you get 135. To see if this is qualified for us to use normal approximation, and both are greater than 5. Because if it's not greater than 5, then this the distribution of the binomial may be skewed to the right or to the left. So if you impose something symmetric to something skewed, that approximation will not be good. So that's why we have to screen. We have to check, okay, with this criteria. Okay, so with that, then we come back and look at the mu, which is MP115. Sigma is square root of MPQ, okay, 7.88. Then we use standardizing to transform it to Z, and then can use a Z table, or if you don't use Z table, you can use Excel. You can easily get the same result. Okay, so this is the approximation of okay. Okay, sorry. We are not using sample mean here because we are just normal approximation to a binomial distribution. Sorry, I was because we followed this section immediately after the previous one. Okay, this is just to use normal distribution to approximate the binomial. Okay, so quite straightforward. And so let's look at the homework question, which is pretty simple because I wanted you to start spending time on the project. Okay, so here we see we use normal approximation to find the probability of obtaining at least 90 heads in 115. Is a normal approximation valid? Okay, so you should find. So what is so what is the so you have to calculate. Okay, 90 heads in 150 is a fair coin. Then the probability, find the probability of obtaining at least 90 heads in 150. Oh, okay, so n is 150, a fair coin, so p is 0.5. P is 0.5. Okay, so you have to check if n is 150, p is 0.5. Is NP greater than 5? Is n 1 minus p greater than 5? If so, then you can continue to calculate the probability that x greater than 90. The probability that x greater than 90, then you refer to this question. Okay, greater than. So greater than, that means is lower bound we minus 0.5 to that number, same number, and minus mu. Okay, mu is what? Mu is n times p. Mu is n times p. Here you have what? N is on 150, p is 0.5, and then divide by that NPQ, square root of NPQ. So you get the probability z greater than the value, and you calculate that probability. That will be it. So this question is also easy. And so with that, you can, you should have more time to prepare prepare yourself to get familiarized with the R code and see how you can use it to calculate the problem. Okay, the problem for our project, the midterm project. Okay. All right. Okay, I probably chose not a time that's best for everybody, but don't worry, you still can listen to the recording. Okay. If you have any question, welcome to make a post and I will help you out. Okay. Okay, I think it's a good point to stop. Okay, let me know if you have any questions. All right, good. Okay. Have a great weekend and see you next week. Okay. Bye bye.